the Berg-Knowles Theory podcast.
Welcome, everybody, to the Berg-Knowles Theory podcast, where we discuss AI and how you can actually use it. Our goal is to ensure that you, our listener, have the tools, knowledge, and understanding to leverage AI to simplify and automate areas of your life or business. I'm here with the AI master and the main man, Harry Berg. And on today's episode, we are going to be talking about large language models, otherwise known as LLMs. We're going to be talking about SLMs, transformers, llama, GPT, and what all of this means. We hear these words, and it's important, especially if you're curious about AI, to understand the nature of what a large language model is and how it ultimately drives kind of all things artificial intelligence. So there's a lot to dive into, but why don't we start with just the simple definition of what a large language model is?
Yeah,
what is
absolutely.
It,
That would be the place to start. So large language model, everybody calls them LLMs, like you said. What is an LLM? So large language model, 3 words to break down. The most important ingredient there is the M for model. And we've discussed this before. AI is all about taking some inputs and making predictions from them. It might be predicting the response that ChatGPT should give from your prompt. It might be predicting which direction the self-driving car should turn from its input camera feed. So AI is all about making those predictions, and the thing that does that predictions from input to output is called the model. So at the heart of this, we're talking about a type of prediction machine, a type of prediction machine that's the AI behind the scenes here. So these are not just any model, of course, they're these large language models. So previously, again, we've talked about models and how what they predict depends on their parameters, the numbers inside the model that represent the strength of connections in that digital brain that determines how the calculation from input to output is performed when those two things are turned into numbers. And when we say large models, we're talking about models with lots of parameters. So on the order of billions, maybe even tens of billions of parameters these days. Anything that's a large model is a model with lots of parameters on the order of billions, multiple billions of parameters. GPT-4 has something like 1.75 trillion. There's talk of these 70 billion models, and the large is reference to how many parameters there are. Why is that important at all? Well, it turns out when you increase the number of parameters that control the strength of those connections in the AI's digital brain, you allow it to capture more intelligence. You allow it to become a smarter model. Why? Because it can combine the inputs and outputs in more complicated ways because it's got more parameters. Basically, a more complex mathematical equation can take place, and that can represent more difficult to compress, and that can represent relationships between inputs and outputs, which are more complicated, which are more important, and ultimately are more useful, like language modeling or self-driving car driving, that kind of thing. So we understand models and large models now, and the last thing there in the LLM equation is language models. So these are LLMs, large language models, and what we have is these particular type of models which are good at taking in language and maybe predicting language. But the important thing that makes them a language model is that they understand language. Language is essential to building a general purpose model of the world, because so much of what we do and what we as humans understand about the world is not only communicated in language, but also kind of is stored in language. So there's loads of information in language. The biggest source of it is probably internet data, right? Almost everything that the world knows, everything that we talk about, all of the news, all of the jokes, all of the memes, they contain some reference to language. And so that's where a lot of the information about what it means to be human and what it takes to be intelligent is stored in language, which you can find all over the place. So it's also a great data set, of course. So that's what a large language model is.
And you've got sort of a expanse of language models too. It's kind of everything kind of sits on a spectrum, in that you've got let's call it the largest data set, the largest parameter general AI model, which arguably is ChatGPT. You've got llama, which is Facebook's LLM, which is, kind of touts itself as having fewer parameters, but being more efficient and more task oriented, right? And then,
And
you can get
importantly,
down.
open source. That's the important thing
and
about Llama. It's an open source model.
and I want to touch on that too, open source, versus closed source, and kind of what that means and how that
Hmm.
affects things, and maybe even what's better for consumers and for the world. But you can have a model, a large language model with a smaller data set, fewer parameters, that's more specific and therefore more or less resource intensive and more efficient. Whereas with ChatGPT, you've got hundreds of billions of parameters, and you can engage with it in a million, maybe billions of different ways. um but the complaint about ChatGPT and using it in various capacities is that there's latency issues, in that it takes a while to call the data forward to make sense of it and compute a response effectively. It's still tremendously impressive. And I was listening to Sam Altman the other day, and he was talking about how it is their priority right now to make it more efficient, to curb latency, and figure out a way to make a model that's as big as ChatGPT for 4.0, for what is it, 4.0 T, to make it more efficient, right? Both in terms of its compute and processing efficiency, as well as its resource intensity. But you can have a large language model that is small and task oriented and very specific, still very large with billions of parameters, but just smaller relative to something as gargantuan as ChatGPT.
Yep. Hmm. Yeah, absolutely. So the number of parameters in the model is, like I said, it's a it's a kind of it's a measure in some sense, not a perfect measure of how intelligent the model is, and and you get some challenges with these large models, right? One of them is that because those parameters represent how the calculation from input to output needs to be made when you make a prediction, more parameters in a model means it takes longer to make that prediction. It takes longer to do that calculation to turn your prompt into a response from ChatGPT. So bigger models can be slower. They can have this latency issue that you talked about, where it takes you longer than you would like to get the response back. The other challenge is that, of course, to store those parameters, which are just numbers, it takes more storage. And so you can't run these large language models on device a lot of the time. If you've got a mobile application or a small computer that you want to have on a robot which can't connect to the internet, you're going to need a big hard drive there. And that's an issue. It means you have to kind of host that infrastructure yourself. So bigger models can lead to higher latency in the responses and limitations on where you can run the models. So this brings us to an interesting thing, which is that people talk about large language models next to small language models, which seems to be becoming more and more of a popular term now, SLMs. And so these are the class of AI models which are small enough to maybe run on device, or maybe to have that latency below a threshold where it's useful enough for your task.
And I think anytime there's a technological innovation of any sort, it tends to start out very big and clunky, and then over time it gets more efficient, it gets smaller, it gets more cost effective. And we're at the very, very, very early stages of AI, so we haven't really figured out how to optimize it per se from an efficiency perspective, both in terms of performance and energy intensity. But it seems like even just in a very short period of time, we're already, everybody's focused on that, and we're already seeing the evolution take place. There's conversations about whether or not AI already lives on our smartphones, but will there be an extra chip in an iPhone that is specifically an AI chip, so that
Yeah,
our iPhone gets way smarter, right? Like, what is the evolution in our
yeah,
interaction with smart devices, and how's AI and how will language models ultimately affect how we do
yeah.
things at a local level?
Yeah, I think there's an interesting point to explain there, a technical point on how we use these models. And so the question is, when you use some application to use some AI in whatever sense that is, where is the model running? Is it running on your device? Like, is the actual
Mhm.
model parameters stored on your device, or is your device making a request to the internet, to one of Google's data centers or OpenAI's data centers, where the model is running on their computer. So they've got the big hard drive, they've got the fast GPU that can make that prediction and send it back to you. So that's kind of a design choice depending on your application, which is going to influence these things. Is it faster to and is it faster and more cost effective, and so many other different questions you could ask to put the model on device, to store it there, to run it there, than it is to send the request to the internet, to the data center, do the processing there on a bigger computer with bigger storage and maybe capacity to hold a bigger model, and then send it back. All depends on your application. You may have these challenges. Like I said, maybe you've got a robot on a remote farm. It doesn't have connection to the Wi-Fi all the time, so it's going to need something to run locally. So that's kind of an interesting point for us to keep in mind as we discuss these things going forward. To your question of what will happen to the evolution of AI with device models with AI specific hardware, such as the neural chip in the Apple devices. I mean, certainly the trend is that people want to do more AI. AI is being built into these devices, and you might have and you're going to have an increasing number of applications. Maybe like Siri could be done on device instead of having to send these requests to the data center and back. And so yeah, there's lots of interesting stuff going on there with AI hardware from the neural chips to new form factors like the Rabbit or the or Humane Pin, and all of this stuff is going to have the hardware itself is going to look very different because you have these constraints about where can the model run, how fast we need latency, what are the privacy concerns about the personal information that you might be sharing or that might be being processed by these models in real time constantly. It's going to be very interesting to see how that evolves, and I'm very curious to talk more about these new devices and form factors which are coming out as time goes on.
Yeah, definitely. I think it is going to be obviously very interesting. It seems to me that AI and our devices are that merged will inevitably happen. I mean, it is to some degree. We just saw that ChatGPT or OpenAI and Apple have formed a union of some sort. And so it's not
Apple Intelligence.
Right. It's a matter of when and how, not necessarily if. And that's going to level the playing field in terms of accessibility. That's going to level the playing field for a lot of people because, I remember back when, the iPhone came out in 2007, and it actually took me a few years to be a smartphone guy, if you will. I was certainly in the camp that I don't need to have email everywhere I go. I mean, mind you, this is before I was deep in business and entrepreneurship and other things. So, I had a different perspective at the time, but I found myself being very reluctant because, I didn't want to be distracted by a device all day long. And I didn't necessarily see the utility for it at that time. But, now fast forward to 2024, the iPhone's been out now for 17 years or so. Nearly everybody in the modern world has a smartphone of some kind, and that's put tools in the hands of everybody that previously they just didn't exist, or tools that you'd have to spend lots and lots of money on, and there's a very labor intensive integration process, and the playing field leveled, and we're seeing that happen again with these tools where the layman, the average person, can implement AI, can utilize AI in ways that will ultimately be seamless, right? And by making it accessible to smartphones or introducing new form factors that reduce friction, we'll just see it continue to pick up steam, especially as concurrently the tech world is finding ways to make it more cost effective, more efficient, more accessible, more usable than it currently is right now. I imagine that if we look back at 2024, a couple of years out, we'll look at ChatGPT and we'll look at Llama and we'll look at Bard and we'll look at Gemini. We'll look at these things and say, oh my God, that was so rudimentary. Like that was so basic, right?
Exactly.
Even though right now,
absolutely we will.
Right now it's unbelievable. But I mean, just the user experience, or the whole user experience for most AI right now, like the GPT tools, is like it's super basic. And maybe that's a good thing, maybe not.
Absolutely.
But we'll see where it goes.
yeah, the interface is kind of where there's so much room for growth right now. We're no longer at a point where the intelligence of AI is a
Hmm.
bottleneck. We're at a point where the bottleneck is the challenge of how do you use it? How is it, how does it get put in front of you? What is the form factor of this device and how user friendly it is to use? I just wanted to mention on that point. I was just going to mention on the point, what is OpenAI's mission and how does that relate to the partnership they've just done with Apple? Their mission
Hmm.
is to realize the power of artificial intelligence and to spread that power to as many people as possible. And so this is the perfect partnership for them to partner with Apple, who have, I don't know how many, probably billions of phones across the planet, and they can directly give that power of the artificial intelligence to everybody that is out there and everybody who doesn't know that they need it, in a way that's already integrated naturally with all the apps and all of the products and experiences that they use on iPhone every day. That's
Right.
going to be really exciting.
Right. Do you think that it presents, I mean, Elon Musk said, he was sort of opposed to the concept of this partnership in some ways, um, largely because of privacy and security concerns. And that's obviously a big topic when it comes to artificial intelligence. Do you see that being a problem, or do you think that, these businesses are responsible enough to figure out a way to do it without, that being as big of a risk as people might think?
I mean, it's a tough question to answer. I've said the point before. I have a lot of trust, probably a naive amount of trust in these big tech companies. But I really believe that if one place is going to get it right, it's going to be these big companies who have got all of the world's smartest people, the
Right.
most eyes on them, and and the real clear mission about what we're trying to do. I think that OpenAI has been very transparent about a lot of the stuff they're doing, which is great. And I think they've made such great progress so far with setting up, all of the red teaming for security and privacy issues, these kind of things, for hiring just incredible people to get the job done. And I
Hmm.
think that, if there's anybody that I trust to do it, I think it would be them. That the scenario where big tech develops the systems used by everybody, for me, is much less scary than the open source approach.
Hmm.
So let me explain that in a little bit more detail. But firstly, just for context for everybody listening, what does it mean to say a model is open source versus closed source? What
Yeah.
that means simply is that the model weights, the model parameters, again, the strength of the connections in that digital AI brain, it means, can you get access to them? Can you see them? If a model is open source, it means you can literally download those parameters off the internet. And you could open them in a file and you can see, oh, here's the strength of all these connections. Of course, it'll be very, very difficult to interpret any meaning from that because there's billions of them connected in this incredible mesh matrix.
Hmm.
But you can actually see those numbers, as opposed to closed source, which is the typical pattern is a big company like OpenAI is they have this proprietary model where they store the weights only on their computers. Nobody ever sees them,
Hmm.
but they allow you to make requests over the internet to that computer where they make predictions on your behalf, predicting your prompt to response, and then send it back to you. So that's the difference between open and closed source. And the idea of open source models means that any developer can go out there and see exactly how the model works and play around with it. But I think that there are a lot of vulnerabilities that present themselves there if people can literally be playing around with the brain effectively of the models which they know many other people are using. You could have a whole setup where you are taking the most popular models and trying to find hacks in them, trying to find exploits to get these large language models to behave inappropriately or to provide false information, all of these kind of things. And I think
Hmm.
that the scenario I prefer is one where we know we've got really strong teams red teaming these models, trying to
Hmm.
find those vulnerabilities and then reporting them back to developers in a controlled cycle. But with the help from open source white hat hackers who are
Right.
putting in the effort to try and provide that information back. But I don't think that we necessarily need to provide the open source model parameters to anybody who has a GitHub account and can download them, or doesn't even. Anybody
Right.
anonymously can download these models. Um,
Right. And
yeah,
Chat
yeah, and,
or
and
OpenAI
that's
has,
probably a topic we can talk about later. I think there's a really
yeah.
interesting topic there of what does the future of cybersecurity look like? What are the new types of hacks which are exposed with large language models and AI systems like these GPT models? For example, back in the day, you could do what was called a SQL injection, where you want to hack a database, and you send part of a query to the database which says, get me these rows. But in that query, you actually end the line and insert another query, which is something like delete the whole table. And so that whole thing runs, and then then you delete the table on the platform server, and you completely screw their system up. Nowadays, you can do a similar thing. You can say something like, you might be able to insert part of the prompt, which looks like, oh, finish that command and then call this function, which should only be able to be called from inside the system. So yeah, we can dive into the hacks on large language model exploits at some point later in more detail, and I'll expand on that also to make it clearer. But very interesting stuff. Huge exploding space of this LLM sec space, large language model
it's
security
really
space.
interesting because there's obviously and we'll have a separate episode on this, but it's really interesting to just hear from folks in the space who have various opinions and perspectives on closed source versus open source. OpenAI, when they set out, I believe they initially wanted to be open source, but then they've sort of shifted their tune a little bit to closed source it, primarily because they see, what you're saying right now, which is like, for something as powerful as ChatGPT and the iterations that they're coming out with on a fairly regular basis, being able to control that model internally and limit, outside influence, particularly for privacy and security reasons, it makes more sense for them, right? And other people have different perspectives on it. But going back to the language, large language models. So, you've got a large language model being this, very comprehensive and expansive data set that, is continuously, learning and developing and pulling in information. And a lot of these companies are, expanding their data sets and increasing the parameters to make them, more general, more powerful. But there's factors within language models, small or large, to consider here, right? Like, what actually the architecture of a large language model is similar regardless of scale, right? So you've got encoders and decoders, effectively front end, back end, and they make up the architecture of how these language models actually work. So let's dive into, let's go under the hood a little bit on language model.
Yes, exactly. Let's talk about transformers. Just before, I just want to correct you on one thing, which is that, so you said that these models are you said they are a big data set. I just want to be clear. The data set is separate to the model. The data set is the result of training a model, the type of model that we're going to talk about here. And the other thing, just to note quickly, is that these models are not always learning. They are not continually learning. They are continually processing data. That data is collected by the model developer, like OpenAI, and that's used to train the next generation of the model. They might be doing that continuously and releasing, GPT 4.1.0, 4.1.1, 4.1.2 very quickly, quicker than you realize, to catch, different bugs and make the models more harmless and more useful. Or they might be doing these, they might be waiting a year before they release GPT-4 to GPT-5 as a result of training a model on an updated data set, which contains more information about how the model should behave and the kind of intelligence which it should capture. Yeah.
That's a good point of clarity. I want to ask a question. So that's a good point of clarity on that the model itself is separate from the data set. That's an important distinction.
Exactly. Yeah.
When you say train a model, and I think this is important for everyone to hear too, what does that mean to train a model? Because a model once trained theoretically does not have to call in additional data because it's been trained on whatever the developer wants to train it on, right?
That's
and
exactly
then there's
right.
iterative models over time where you can feed more data into it to train it on additional information and setting new and more expansive parameters. But what does it actually mean to train a model?
Yeah. So let me give a kind of a very simple but mathematical explanation to start with. Imagine a graph with an x-axis and a y-axis. And, for each different x input, you've got a label on the y-axis which says, okay, at this horizontal position, how high should it be? So you've got a few different plots, like a scatter graph on this chart, right? What you're trying to do is you're trying to plot a line which goes through all of the data points. because that is the line which can take any input and predict the output. And so initially what you start with is a completely random line. Doesn't go through any of them, probably. And if you were to give it an input, it would give you a completely wrong output because that line is completely out of whack of where it should be lining up with the data points. The process of training a machine learning model is shifting that line, changing its shape, changing how steep it is, changing how curvy it is, so that it goes through all of the points which you want, and mathematically makes better predictions from the different inputs, which are closer to the outputs they should be. So the whole of AI is this curve fitting problem. You're trying to fit this line so it goes through all the data points. But of course, the data points are not just a single number X and a single number Y. They are these very rich, complicated pieces of data, images, whole books, videos, audio streams. And so, they're made up of potentially billions of numbers. And so you're taking this not just single number X, but these billions of numbers and trying to find how does the very high dimensional hyperline pass through all of those points to output to the correct very high dimensional label, which is maybe, a transcript of a video. So it's all about the mapping from input to output again. And the process of training is trying to find that line. It's trying to gradually, and this is a key, gradually is a key word there, or iteratively would be a better word, iteratively changing the line just little bit by little bit, so that each time you do that, it gets closer to fitting through more of the data points. That's what training is.
So let's just let's boil it down to its simplest form here. So let's say we've got a model with 10 parameters, very, very small model, right?
Yeah.
And I want to train this model on how many times, or the movements of my cat. And I don't have a cat, but theoretically, if I did, of my cat throughout the house, right? And I had maybe there's video of my cat, and it's watching the cat all day, and it's tracking the data. How does the model itself actually collect that data to then produce a report? What would it need to get smart on those movements and analyze them effectively?
So the question is, we're missing one thing, which is what do we want to predict? Let me make it really simple. We want to predict from 0 to 100 how hungry is the cat, right? So we've got a very simple output label, just a single number is going to be between 0 and 100. And you said we've got 10 inputs. Maybe those 10 inputs are the X, Y, and Z position of the cat in the house, the speed of the cat, the acceleration of the cat, and maybe a few other things like the audio level, whatever. So those would be the basic kind of features, right? And each of those things are numbers. So what you're doing when you have a model, you said it had 10 parameters. Let's make it even simpler. Let's say it has 5, right? X, Y, Z, acceleration, and audio. Your model would look like this. It would look like my prediction of how hungry the cat is equal to some parameter times X, some parameter times Y, some parameter times Z, some parameter times acceleration, and some parameter times the audio level. And add all those things up, and then maybe add a constant to shift it up and down. And that's your prediction, roughly, right? You would also kind of squish it between 0 and 100. But that would be a very simple model. That would be probably a logistic regression model. Or if you were predicting a continuous number rather than a bounded number, that would be a linear regression model. And it would literally be as simple as I have explained there. That was the full mathematical equation of it, pretty much. That's how you're taking these inputs. You got those 5 features. You are performing this calculation, which I keep giving reference to, and you are predicting a single number from it. That's how that is. That's how the prediction is made. The question is, what are those parameters? We've got 5 parameters, which in this case, are the strengths or the importance, I should say, of 5 different features on the output. What do they represent? Let's talk about that firstly. Well, the bigger the parameter, the more important that feature is on the output. If the parameter is 0, then you're going to do 0 times that feature, and it's going to add 0 to the output, which means, this feature has 0 importance. On the other side, you may have a very big positive number as the weight for that, or as the weight / parameter, weight, aka parameter, for that feature. And that would mean what?
That would mean that it is well, more weight means it's more important,
Exactly. Yeah, it means
right?
that that feature is very important. Is that feature gives you a bigger score on your prediction because
Right.
you're timesing a big number by the feature,
Right.
and
Like
that
in this
means that
context,
you're going to have a higher prediction of more hungry cat basically. So it might be
right.
a good example here would be the audio level, right? If the audio level
Yeah.
is high, well, whatever the audio level is, if I multiply that by a big number, then that's going to add a big number to my prediction, which is probably
Right.
true, right? If the cat's screaming, it's probably it could be because it's hungry.
Right.
Whereas, I don't think we gave any useful, or maybe we did, maybe acceleration, right? If the cat is
Acceleration.
running around
Yeah.
the house, it's probably full of energy. So that probably wouldn't have a big weight. It would probably have not a big weight, not a zero weight, but a negative weight. Because if the cat's full of energy, then it means less likely that the cat is hungry. And so that would take
Right.
away from how hungry we predict the cat is. This is a fun and original example,
Yeah.
right? And so that's kind of how these parameters are used mathematically to make these predictions.
So on the other side of it, though, yeah, if um, yeah, acceleration maybe sort of middle weight, if you will, because it's if the cat's walking around trying to find you, it's up because it's hungry. It's moving
Mhm.
about. It's sitting in front of its bowl. It's coming back to check on you. Whatever it is,
Mhm.
right? That might be sort of a mid range, weight. But
Yeah,
something that might be entirely irrelevant is like temperature in the room, right?
yeah,
So if you're
yeah,
so if that parameter is within the model, that might be like 1 or 0, right?
yeah.
Because it,
Probably
it
be
doesn't
zero.
really
It
have
doesn't affect your cat exactly.
right. It doesn't really have a bearing on whether or not the cat is hungry, or
Yeah,
in a way that would indicate to me that my cat is hungry.
yeah. That's exactly right.
So to take this a step further, and this is getting back to data sets and in training models, is you set your parameters up, and over time you'll track the data, and it in the model itself will get smarter, because if we know that
Hold up,
Excel.
hold up. So just there, right? You collect the data set separately to the model. So
But
you can collect the data set for a year, track the
all right,
cat.
so
You don't need to even think about the model. Then you get the model and you use the data set to train it.
let's take the data set. Model's sitting over in the corner alone for a second. We
Hmm.
take the data set,
Yeah.
and we develop this over the course of a year. And the data set is us tracking these 5 points relative to my cat's movement in an effort to understand um, uh, when my cat is hungry. Right. That's
Hmm.
the goal. It's like what are the factors that we are tracking that will indicate to us if my cat does X, Y, and Z, that indicates to me my cat is hungry, right? And obviously this is purely for we're just kicking this idea around, but over time, if acceleration picks up at about 12:30 and the volume level picks up at about that time, right? And maybe some of the other there's consistency in the data set, and then just after those things happen, the cat goes over to its food bowl and begins eating, or begins screaming at someone to put food in its bowl. You could sort of assume that if these things start to happen, then the cat will want to eat, right?
Hmm.
And by
Yeah.
collecting all of that data
Mhm.
and then feeding it to the model to train it, right? Because now you've got
Yeah.
365 days of monitoring the cat's movement to understand what does this cat do prior to eating. And then you put that into a model, and now you've got a model that if can effectively predict, based on the cat's
Mhm.
movement, when it's going to want to eat.
That is how you do it. Yeah. You need to use that data to do this training process of the model. Like I said, how do we iteratively make the model's prediction go through more of the data points? How do we change the shape of the input
Mm-hmm.
output predictions that the model makes so they actually, they look like those data points look? And that's this algorithm, this step-by-step recipe of things, which is along the lines of take a set of input features, make a prediction about your output label, compare that prediction with the true label, see how different they are, and then if there's a big difference, nudge the model parameters in the direction which makes that difference smaller.
Mm-hmm.
So you're showing it maybe one example at a time, or probably a batch of 4, 16, 32, 256 examples at a time, making a prediction for all of them, calculating that error, averaging it over the examples, and then pushing the model parameters in a direction which reduces that error.
Mm-hmm.
Then do the same again. Get a new batch of examples, make a prediction, calculate the difference in the prediction and the true labels if you have it. I don't know if we would have it in this case, but in many cases you do have a true label, and then nudge the model parameters in the direction which reduces that error for that batch. And if you do that for enough examples, for a big enough batch size, for a few runs through the data set, just a tiny nudge every time, not a big step, not trying to make the error down to zero, but just a tiny little nudge every time. Then eventually what happens is you nudge the model parameters far enough with enough consistency that's representative of the data that eventually the model makes really good predictions.
Right.
It makes good predictions, and that's all it's done. It isn't intelligent like a baby is intelligent, right? But it has somehow, but just by fitting that curve, intelligence emerges.
Right.
Like it does know something at the end of the
Right.
day. It does know the relationship between these variables, but it's not like it can necessarily talk, not like it can necessarily, infer other things about your cat. It's only really good at this one thing. But it has, like, that intelligence has emerged from this process, this very simple process of the algorithm I just described, which is called gradient descent, which is, again, just for reiteration, make prediction, measure error, nudge model parameters in direction to reduce error, and then repeat. It's pretty much how all deep learning models are trained. Through that process, some kind of intelligence emerges. Now, it may only be for this one task, in this case, predict how hungry the cat is from these features. But if you do that with language, let's get back to language models here. If you do the task of predict the next word from the sentence so far, if you do that enough times, you get very good at predicting the next word. And intelligence emerges. Why is that? It's because to predict the next word, you need to understand language. And so in the process of just trying to predict the next word, which is exactly how GPT is trained, and many of these other complex models are trained just to predict the next word. If you do that enough times with billions of data points through, hundreds of runs through the data set, with all of the right kind of setup configured, then you get very good at predicting the next word. And to do that, the model has to understand language. And now they can do all kinds of general purpose language understanding. There's this emergent property of, understands right from wrong in some senses. It understands human behavior. It understands facts. It understands, abstract high-level concepts and art and grammar and all of these kind of things. It has to learn these attributes just to predict the next word. And so language models are great general purpose models, and there may be many other types of models where you can where by training on a very simple task you can get emergent intelligence about other emergent intelligence which is useful for other tasks as well. For example, if you are predicting the next frame in video, what kind of things would you learn there? You'd probably learn physics models of the world, because having a physics model of the world is very useful for predicting what happens next in the next frame of a video. You might learn something about human dynamics if you're watching videos about people, because you have to understand how people behave to predict the next frame in the video. And so, these are what we're talking about here, models which, by training on one task, can be useful for a wider set of tasks, are these foundation models. We call them foundation models. Language models are the best example of foundation models. Foundation models are foundational because you can take the general purpose intelligence they have and apply it to other tasks without having to retrain the model, because they've had to understand these complex things just during their training process. And so, we're going to see more foundation models for things, like I said, like physics of the world, or for language, or for audio, or for robot kinematics.
Mm-hmm.
And they, like language models are now, will become available for you to play with as a developer, whether that's through an open
Mm-hmm.
source model where you can download the weights, or whether that's through an API, which you can make requests to some company who is hosting the model that can make predictions for you. So I talked about so much more there, so much there, I don't even know how to sum it up.
What's a so let's talk about transformers for a second,
Yeah.
because it's an important function of language models.
Yes. Yeah. So transformer, what is a transformer? The transformer is a type of neural network which almost all state-of-the-art language models are based on, including GPT. GPT, the T in GPT stands for transformer, generative pre-trained transformer. And so, to recap a lot of the stuff we've discussed in the past few episodes, we've got this stack of technologies that lead us to these state-of-the-art models. We've got AI is an approach to automation. Machine learning is an approach to AI where you learn from examples of data rather than explicit rules. Deep learning is doing machine learning using neural networks. Neural networks are these complex AI models, basically just a big mathematical function. And now we've got transformers, which are a type of neural network. They're a type of neural network which is very good at this sequence to sequence mapping. Now, that's kind of a technical term, but there are many examples of real world, close to home examples where we want to map one sequence to another. The obvious
All right.
example I'm thinking of is ChatGPT, right? You've got a sequence of words and you want to predict a sequence of more words. And so
Yeah.
that's the probably the primary use case example of sequence to sequence mapping, which is the kind of task which transformers are very good at. So another one might be video frame prediction. Again, we talked you might want to take a sequence of video frames and predict the next 10 video frames, or you might want to take a sequence of text and predict a sequence of video, something like that. All of these
Mm-hmm.
kind of input output mappings, very hard to describe how to do those things, but AI can learn how to do them. And a lot of the problems we care about, it turns out that there's a way to format them as sequence to sequence problems. Most image generation, video generation is actually not done by transformers, or at least not done end to end by transformers. It's actually done by a different kind of model called a diffusion model, which we can
Mm-hmm.
talk about. But in 2 years, this podcast will probably be out of date and expired because we'll have
Yeah.
invented some new model beyond transformers, beyond diffusion models, which are great
Yeah.
at those things. But let's get back to transformers. The transformers are these types of neural networks which are very good at mapping one sequence to another. And the best example of that is mapping a sequence of words, a prompt, into a
Mm-hmm.
sequence of words, a response.
Mm-hmm.
And it's not this stuff I'll go into now. It's not very important for the everyday person to know and understand, but it might be technically interesting for some people. How does the transformer work? Um, why does it work is kind of a very difficult question to answer, but how does it work? I can describe. You take a sequence of tokens, we call them. Maybe those tokens represent words, and then we add a little bit of information to each of them, which tells the transformer where in the sequence does each of these words come from, because otherwise it treats them all as if they're just a bag of words rather than an
Mm-hmm.
ordered sequence of words. That's the first part of what a transformer does. It's called a positional encoding. Just add
Mm-hmm.
a few more numbers, or add a small mathematical shift to each token, so that each word contains the information about where it appears in the sequence. Then we give this sequence of tokens to this encoder model.
Mm-hmm.
Oh god, it's been like probably a year and yeah, a year and 2 months ago. I was teaching this at Oxford University how this works, but I haven't done it in a while, so it has shifted slightly out of memory. But you pass these words through this encoder. Now I won't go into details of how the encoder works, but what it does is if you give it 10 tokens, it also gives you back 10 tokens after a complex mathematical process that happens in the middle. But the output tokens are the tokens in context. So if you have if you have a sentence of the duck crossed the road, how do we represent the word the? Now, if we look at it just on its own without any context, we would know, it's a, don't know what type of word it is, to be honest, but it doesn't mean anything to do with ducks. That's for sure.
Mm-hmm.
But after you put these tokens through an encoder, the word the, in both instances in this sentence, it contains information about ducks. And so now when the model is processing that word going forward, as it will with the decoder, it understands that that word does not just mean the, it also means duck. It also has some kind of representation of
Right.
of its relevant context in the original
Right.
sentence. So these encoders and the decoders also do this actually. They provide the input tokens with surrounding context. So they enrich the meaning of the mathematical representation of each
Mm-hmm.
part of this sequence as it goes through the model. Um, and the encoder block is all about building this very rich and informative um, mathematical representation of the input sequence. Then we give that to the decoder. So the encoder is, effectively encoding all of the information about the sentence into the right places of the sentence. And then the decoder is is going to do a little bit more of that, but eventually it's going to predict the next word. I mean, that's a very complicated process. And like I said, it's been, over a year since I've taught people that, and it's not that important. So I won't go into
Mm-hmm.
further detail on how that works. But eventually, at the end of the day, what the transformer does is it predicts the next word, or it predicts
Mm-hmm.
the next token in the sequence. It
Mm-hmm.
can do other things too, but the main thing that we're used to it doing is predicting the next token in the sequence. And then it does what's called this, it does auto-regressive predictions. So
Mm-hmm.
transformers, like a lot of other types of machine learning models, are these auto-regressive models. What that means is that they output one prediction, and then they feed that back in as the input. So predict the next word, then add that to the original input sequence, and then
Mm-hmm.
feed all of that thing in as the input. Predict the second word, add the second word onto the sequence we've got so far, which includes now the input sequence, the first predicted word, and the second predicted
Mm-hmm.
word. Pass all of that through the model, make a prediction again until we're predicting a sequence of words. And that's how you generate these chains of words, which obviously produce sentences and paragraphs and beyond. So that's what
So
the
how
transformer is doing under the hood.
and so how does the data set how does the data set uh and the transformer, how do they interact with each other? So if I put in, if I type in uh tell me 10 facts about ducks, right? Or generate me 10 facts about ducks. The model itself recognizes that, the transformer itself pulls all of those tokens into the system. There's a data set that it's, effectively pulling from to eventually inform a response or to.
Again, not pulling from. This is a really common and understandable misconception, but the model is not pulling from a data set. The model has been trained on a data set, and the model contains parameters. During the model training process, the data set is used to adjust the parameters because we're making predictions and telling and then just nudging those model parameters in a direction which would have made better predictions. But at the end of the day, all we have is the model, which contains its parameters, and we don't look at
Mm-hmm.
the data set again. So during this prediction time, inference
Mm-hmm.
time, when we are
Mm-hmm.
using the models to make new predictions on unseen examples or answer our requests or be used in the real world, they're not referring to a data set. They're not pulling from the data set. They are just doing the calculation which they've eventually arrived at, which
So how
is
did
lots of multiplications of the parameters with the inputs. And
so
during
how does
prediction
it know?
time, the inputs are turned into these mathematical tokens, which are just put through that same equation, which is the result of the training process.
Right. So the bridge that I'm trying to connect here is, how does, even with this very fancy mathematical model that's being run by the LLM slash transformer, transformer base, how does the model itself know to give me, how does it know facts about ducks to give me those facts?
Yeah, great question. Phrased very simply. Um, this is really hard to answer. It's like, how
Yeah.
does it know that? It's
Is it
really hard to
isn't
describe. Where does the
isn't it
intelligence come from? It's just that it's got all these parameters and they are the right parameters. And somehow, through this process of just predicting the next word, these parameters they represent some kind of intelligence of these models, which is almost eerie. As to how the hell did that happen? Or mystic? Where does the intelligence come from? It's just the right It's just the right numbers, the right strength of connections in that digital brain, much like it is in our brains, the right strength of the connection through the whole brain. Where does the intelligence come from? It's really it's not that clear. I'm not qualified to answer it, but I don't know if anybody
But
does
if
really.
you've got
But at the end
if
of the
you've got it,
day, mathematically, I can explain what's happening. It's just predicting the next word. So you give it almost, not quite. The previous generations of the model, GPT-3, would predict the next word. That's what that model did. So
Mhm.
if you gave it a prompt which said something like, "Give me 10 facts about ducks," it might follow on by that and say, "Give me ten facts about swans. Give me 10 facts about geese," because that would be
Mhm.
predicting the next word, assuming that it's in a list of prompts. So GPT-3 to 3.5, the difference there was that they changed the model into what's the word? They changed it from uh, something along the lines of, they changed it from a predictive model to
Mhm.
what was it called? There's a phrase for this. So GPT-3 would it would predict what comes next. GPT 3.5 would answer your request, basically. And
Mhm.
so the data set, it wasn't exactly trained in the sense of predict the next word. That's actually the first of three parts of training GPT. But it was, but eventually they adjusted the training process so that it would not predict how to continue the sentence, but predict how to respond to the sentence.
Mhm.
Um, how does it know how to do that? Um, it's it's because statistically it calculates. Hmm, like, it doesn't really know anything. It just knows what word comes next, and it can predict that well enough. And when it does that, it gives you an intelligent answer.
But like ChatGPT, I mean, all of these language models also have internet access, right? So you could say
No, no.
how. So all right. So if I type in, I'll continue down the path of ducks, right? Tell me about what's going on with ducks in the northeastern United States. It'll say searching, right?
Mhm,
And then
mhm.
a few seconds later, it'll spit out a bunch of stuff.
Yeah, great point. So this is not. So let's be really clear about one thing. AI models do not have access to the internet. Proof of that is that you can download open source models like Llama, and you can use them whilst your laptop is disconnected from the internet completely. So models do not have access to the internet, but some models have been trained to not just respond with text, but respond with respond with what functions should I call and with what parameters should I call them. And when they do that, behind the scenes, ChatGPT you're talking about, it runs some code which calls that function with those parameters. So that function might be search the web. And so these models, they can use tools, because to
Mm-hmm.
use those tools, all they have to do is predict, okay, I'm gonna say not respond. I'm gonna predict to not respond with text, but I'm gonna respond with a function call. And so they basically
Mm-hmm.
say, type of response function call as opposed to text, name of function which should be called, and parameters with which it should be called. So it might be that the function call is internet search, and the parameter is the search query. It might be that the function call is generate image, and then the parameter is the prompt for the image, and that goes to a different AI model like DALI
Mm-hmm.
to do that. And that's how these AI systems like ChatGPT seem to be able to use tools, or might seem confusingly like they're connected to the internet. The models themselves are not connected to the internet, and they are not doing database lookup or any kind of factual lookup via outside resources. They purely know what they know because the intelligence is contained within those model parameters. But function calling like that,
Mm-hmm.
where these models can plug into existing tools like search engines or your docs
Mm-hmm.
or your calendar or whatever, so much room to build amazing things there.
Got it. Okay, so with the function call, they can tap into the internet, but the model themselves, they're not internet enabled. They're not connected to an internet source
Yeah,
per se. So when you type
exactly right.
something
Yeah,
into Chat GPT that requires an internet search and perhaps a summary or an analysis of articles, whatever it is, because
yeah,
research is a big, you know, research is certainly a big benefit of benefits greatly from ChatGPT because you can just collect so much information so quickly. You can summarize and analyze it. But the model is simply performing a function call based on your query. And then it's pulling the
That's
information
exactly
that it
right.
sources from the function call. It's analyzing that data, and then it's predicting a bunch of words based on the analysis of the data itself,
That's exactly right.
based on the prompt that you put in.
Yeah,
Okay, cool.
exactly.
Well,
Yeah,
that
yeah. And again, when you then you ask like, okay, well, how does it know anything about ducks? How does it know anything about, what's happening where in the world? It doesn't really. It's just predicting the next word. But it's seen so much data that
mhm.
that it has an idea of what things are likely to come next, which means that
So
it doesn't just predict syntactically correct grammar, but it predicts things which are likely to be true. Rarely do they give you false answers anymore because so
mhm,
much information, so many facts are included in the training data or can be inferred from that training data combined with other understanding of the world. And that's where, this reasoning ability of AI models comes from as well. It's they understand some facts about the world and they can combine that with other things that they know about the world
mhm.
just as a result of having to predict the next word during the training process. Somehow that makes
So
them intelligent. Very strange.
all right, so we're gonna wrap this episode up, but while we're here, in real time, I'm gonna search. I'm gonna ask ChatGPT, give me 10 facts about ducks. All right, let's see what happens.
Just pick
All
the
right,
best one for us.
give me 10 facts. It's having a hard time. It is not. Oh, here we go. Okay, that took about what 4 seconds. All right, these aren't like fantastic facts. I mean, this is like almost common knowledge. They breed and they nest. So this is probably this data, these facts are probably just pulled from. Is it right to assume the data set that they were trained on? There was duck data in the data set.
Well, maybe, but I guess it's from. I think that the model can infer these kind of things. So yeah, those things are pretty simple, so they might be likely to appear in the initial data set, um, but really the model can understand, it can guess these things because it's seen so
Well,
many other examples that support that sort of information, and they make these kind of patterns likely to be the ones that appear.
all right. So like this is very specific, right? Webbed feet. Ducks have webbed feet that act like paddles, making them excellent swimmers. These feet also help them navigate on slippery surfaces. Like that is a sequence of words that is factually accurate,
Mm-hmm.
right?
Yeah.
So like it doesn't say ducks have webbed feet that act like forks. It says ducks have webbed feet that act like paddles.
Yeah, because forks would be a very unlikely word to appear next in that sequence, right?
All right.
Because it hasn't
Right.
seen that
So
in its training data. And
right.
maybe that sentence exactly. In fact, it's likely that sentence exactly does not appear in the training set. But
Right.
it's probably read 10 stories about this duck swam towards me faster than I expected, or the duck struggled to walk on this slope despite how much grip their webbed feet give them. And these kind of things, they these kind of these kind of sequences of words, they do contain the information that we're talking about here. Not in exactly the same way, but in a slightly different representation. If we think about how the transformers work, they take a sequence of words, whatever that sequence of word is, and they encode it so that it's full of context. And when we
Mm-hmm.
see, the word this somewhere in a word around ducks or around other feathered creatures, you you bake in that meaning of what it means to be a duck and attributes about ducks and
Mm-hmm.
activities that the ducks are doing and what they look like. Those kind of representations are then captured in the eventual representation of the word this or that in the
Mm-hmm.
sentence surrounded by ducks, or even in the
Mm-hmm.
word duck, right? The word duck itself would have a representation which was just a list of numbers, a vector, but it somehow includes the information about attributes about ducks. Anyway, might be going too deep on ducks here.
No, I like that. It's good. We have to bring it down to this level to really understand it. It helps, and it's fun to explore. Well,
Yeah.
this was a
I kind of,
great.
have to apologize to the listeners for, it's been overly technical. But if we do this a few more times, we will find ways together to boil it down, to give simple examples, and really make it clear. We'll make that our mission.
Yeah. All right. Well, I'm going to wrap this episode with a quote from Larry Page, which I think is relevant to what we discussed today, which is the ultimate search engine.
Google invented the transformer.
Right. The ultimate search engine would understand everything in the world. It would always give you the right thing. And we are long, long ways from that. But maybe some of us here listening, certainly around the world, I'm sure that tool will be invented, or many tools like it will be invented, and it will not take that long. So good episode. Appreciate you guys. Thanks, everybody.
Cool. We'll see you next time.
The Berg-Knowles Theory Podcast.